Now coming to the next part of the solid state, we are having the elements of symmetry. Now here you have to little bit imagine the things. So I will try to do so. I will try my best. So we are having, let us say, that is cubicle. That is object you are having. Think of, you are having a cubical object, like for example the dice of the Ludo. We can say that you can take it, or matchbox is not exactly cubical, but you can also take that particular and think of. Clear? So what you find is that we are having a rectangular plane of symmetry. You take the rectangular sides, rectangular plane of symmetry. You take the diagonal, then we are having two diagonal plane of symmetry, two rectangular plane of symmetry, and we are having an axis of four-fold symmetry. How many axes we are having? That is 3. Got it? We are having two diagonal plane. So plane will be 1. Now two diagonal will be 2, but the plane will be 1. Understood? Plane means a two-dimensional plane. So definitely diagonal means two lines. In two lines a plane surface is there. That is called a two diagonal plane of symmetry. Means I mean to say two lines are there, but the plane is 1. When I say two rectangular plane of symmetry, means same thing. You take the rectangular sides, again the two lines will be getting, but the plane is 1. So rectangular plane of symmetry is 1, diagonal plane of symmetry is 1, again I repeat, and there is axis of four-fold symmetry, which is 3, which is passing through the middle. We can say that axis of three-fold symmetry is also 4, axis of two-fold symmetry is 6, and the center of symmetry is nothing but 1. We can say that. Now axis of four-fold symmetry, so what is that? Axis of symmetry means it's an imaginary straight line about which if the crystal is rotated, listen carefully, it's an imaginary straight line about which if the crystal is rotated, it will present the same appearance more than once during the complete rotation. It will present the same appearance more than once during the complete that is rotation or revolution. We can say that. How many times it is showing the same appearance? The axis of symmetry is called dyad, triad, tetrad, hexad respectively. Depending upon the original appearance is repeated twice after an angle of 180 degree, thrice after an angle of 120 degree, 4 times after an angle of 90 degree, and 6 times after an angle of 120 degree in one revolution or in one rotation. Thus the axis of symmetry, on that basis we can call it as twofold. Twofold means 180 degree means twice you are getting 180 into 2, it is twofold. So if it is 120 degree, after 120 degree it appears, then it is threefold. After 90 degree if it appears, then 4 times you will be having, so fourfold. And after 60 degree if you are saying the same figure it appears, that is called as sixfold geometric, what you can say, symmetry. We can say that geometry, I am saying, sorry, sixfold symmetry, we can say that. Got it? In general, if the same appearance of crystal is repeated got it, rotating to an angle of 360 by n, we can say that, around an imaginary axis, the axis is called an n-fold axis. We can say that. Suppose you divide, you are having total 360 degree, isn't it? You are rotating that particular figure 360 degree. How many times you are getting the same, what you can say, figure? That is n. So 360 by n will give you the n-fold axis or n-fold symmetry. Got it? Axis is imaginary always. I started with that only. The axis is imaginary. I said you axis of symmetry is what? It's an imaginary straight line about which the crystal is rotated, that it will present the same appearance more than once during the complete rotation or revolution. That is called as axis of symmetry. If it is twice, how twice? If it is coming after 180 degree, so definitely it will be twice. Alright, if it is coming after 60 degree, so definitely it will be 6 times. If it is coming after 90 degree, 360 by 90, it will be 4 times. In this way we come to know. Alright, so in all there are 13 axes of symmetry possessed by cubical crystal like NaCl. We can say that 13 axes of symmetry possessed by cubical crystal of NaCl. Now coming to these elements of symmetry, the total number of planes, axes, which you can see it on the screen. Now see there, the total number of planes, axes and center of symmetry possessed by crystal are termed as elements of symmetry. Total number of planes, axes and center of symmetry. Alright, now I told you 13, that was the axis of symmetry of NaCl. Listen carefully. 13 was the axis of symmetry for NaCl. Now it is the total number. I am talking total number to you. So total number, how do you find it out? Total number you find it out from the plane of symmetry, from the axis of symmetry, and from the center of symmetry, we can say that. So plane of symmetry is, I just now was talking to you, it is an imaginary plane which passes through the center of a crystal and divides it into two equal portions, which passes through the center of the crystal. That just now I was saying, na? So, and which divides it into two equal portions. Got it? Such that one part is exactly the mirror image of the other. We can say that. Clear? So, in this way. So, in case of sodium chloride, I am coming to this only, I am talking about on the screen which you are seeing. The sodium chloride, it possesses 9 planes of symmetry, 3 rectangular planes of symmetry and 6 diagonal plane of symmetry. Total is 9, 3 rectangular and 6 diagonal plane of symmetry, we can say that. Clear? Then axis of symmetry already I have discussed with you, which is 3-fold, 4-fold, 6-fold, which is nothing but total 13. And center of symmetry is 1. Center of symmetry is nothing but, it's such an imaginary point. Center means it's a point. Within the crystal, that any line drawn through it, it intersects the surface of the crystal at equal distances in both the directions. In all the directions, not both the directions, all the directions. You will draw imaginary line, got it, in a crystal. At a particular point at the center of the crystal, all the lines will meet at a particular point. That is called as the center of symmetry. That means a crystal possesses only one center of symmetry. Definitely all the lines will meet at a particular point only. All the lines will pass through a particular point only. That is called center of symmetry. So plane of symmetry is 9 in case of sodium chloride. In axis of symmetry is 13 and center of symmetry is 1. So total number of symmetry elements is 23. In this way we find it out, total number of symmetry elements. Now why did I say you about it? Maybe it may come in your exam somewhere. So you need to remember that how do you find it out. I think you understood it. That is how do you find the different folds of symmetry. Got it? Again I repeat, the axis of symmetry is, because that is quite important. That is, it is an imaginary straight line about which a crystal is rotated. If the crystal is rotated, it will present the same appearance more than once during a complete revolution. Alright. So as a result, the axis of symmetry is called diad, triad, tetrad, hexad. In this way it is being given. Depending upon the number of times it is being repeated, the figure is. Okay. Now, next is calculation number of constituent units in a hexagonal unit cell. If it is a hexagonal, then how do you calculate? So, it is the same way it is only. So, here you can see constituent units at each corner of unit cell is common among 6 unit cells, hence contributes 1/6. There it was, see, it was cubical, na, unit cell was. So, it was 1/8. Because 8 corners were there. Here it is 6. Hexagonal means 6. So contribution to each corner, listen carefully, contribution to each corner will be 1/6 instead of 1/8. Now, constituent unit at edge is common to 3 unit cells and hence contributes 1/3 to unit cell. There was 1/4. Got it? One plane was having 4 edges. So it is 1/4 was there. So contribution to each edge was 1/4. So here it is 3 edges are there. So it is 1/3. For that reason I am comparing it so that you can understand it. Constituent units present at the body centers is considered in a single unit cell. There is, of course, that we do it in cubical also. Constituent units at face centers is common between 2 unit cells, hence contributes to 1/2 to each unit cell. That in face centers also same thing. What is the contribution to each face? 1/2. What is the contribution to each edge in cubical unit cell? 1/4. Here it is 1/3. What was the contribution to corner? In cubical unit cell was 1/8. Here it is 1/6. And body center is 1 only. So you can see the figure is being shown here. Clear? You can go through it. You can understand it. In the hexagonal unit cell, 12 corners are there. 2 face centers are there. And 3 constituent units within the unit cells are occupied. Hence, effective number of constituent units present in the unit cell will be 1/6 into occupied corners, 1/6 into 12, because 12 corners, half into occupied face clusters, which is 1/2 into 2. So, there are 2 face centers are there. And central constituent units, which is nothing but known as the body center, we can say that, which is nothing but is your 3. It's already written there at the top. So, you do it, you will be finding it out, the calculation number of constituent units in a hexagonal unit cell. That is nothing but the value of Z, we can say that, is 6. Got it? We got it as 6, we can say that. In this way, we got the value of what you can say z in a hexagonal unit cell, we can say that. Now in continuing the hexagonal unit cell only, what will be its that is percentage of the space occupied, that is a packing fraction, same 74.06%, but the calculation is little bit different. That let us consider the hexagonal unit of the unit cell which is having a height h, its constituent units are having spherical having radius r. So number of constituent units, just now we studied how much it is, 6, you can see at the bottom, serial 6. So volume occupied in the unit cell will be 6 into 4 by 3 pi r cube. Now volume of the unit cell will be area of base into height. So base is nothing but an equilateral triangle. So root 3 by 4 a square, area of equilateral triangle, into height is your nothing but 4r into root over of 2 by 3. We can say that. Height of the equilateral triangle, isn't it? So now next is, if you multiply it, you will be getting 6 into root 3 by 4 2r square into 4r into root over of 2 by 3. So height of the unit cell may be calculated geometrically, that is being written. So percentage of space occupied will be, that is the volume of the unit cell, that is 6 into 4 by 3 pi r cube, divided by the total value which I said, 6 into root over of 3 by 4 2r square into 4r into root over of 2 by 3. You will get a fraction. Now if you want to multiply, if you want to convert it into percentage, you need to multiply with 100, you will be getting 74.06%. Similarly that of what you can say FCC. For that reason we say FCC, HCP both are same, but the calculation you can say it is being different here. Now these are the examples given of different types of crystal type, we can say that. Rock salt, what is the example I have discussed with you about it in the previous AV. Then we are having another structure, that is a Woodside structure. I felt that I should say you about it. That is Woodside structure. That is, we have different structure. Now we have studied fluorite, antifluorides, CF2. CF2 I'm saying, that is nothing but is your what is that, NaCl, ZnS, all this we have studied, isn't it? So apart from that we are also having this one, that is a hexagonal close pack HCP structure where S2 minus ions adopt HCP arrangement and Zn2 plus ions occupy half of the tetrahedral sites. So above structure has coordination number of 4:4, and the examples of Woodside structure is ZNO, AgI, SiC, etc. So this is now difference between the Schottky and the Frenkel defect is given to you. You can go through it. The difference between Schottky and Frenkel defect, we have discussed upon it. Just I have given this particular one because it will help in your exams to study about the Schottky and the Frenkel defect. You need to understand it. What is Schottky and Frenkel defect? Got it. This is all about, we can say that. Thank you.